Hello everyone, I'm Sudha Udaya. Welcome to today's unit in the Building and Construction program. Before we begin, I want to remind you of the purpose of this program. Each unit is designed to give you the knowledge, skills, and industry behaviours required to become a competent and confident building practitioner in Australia. Throughout this course, I'll be drawing on more than 30 years of hands-on experience in residential and commercial construction. My goal is to connect the theory directly to real project situations, showing you how the National Construction Code, Victorian regulations, WHS requirements, and industry standards apply on actual work sites. As we move through each topic, think about how these principles translate into the decisions builders and site managers make every day. By the end of each unit, you should feel more prepared to apply these concepts in practical, safe, and compliant ways on the job. Let's get started. This session covers CPCSUS4002. Use building science principles to construct energy-efficient buildings. In this presentation, we'll link building envelope expectations, key building science concepts, and construction method decisions so the finished building delivers comfort, health, durability, and lower energy demand. This unit is about applying building science during construction, not just at design stage. It focuses on selecting suitable materials and systems, following correct installation methods, and checking critical details on site so energy performance and durability are achieved in the as-built outcome. By the end of this session, you should be able to determine the building envelope expectations, assess energy efficiency construction, decide on method of construction, identify type of use and energy. Efficiency, expectations of the building. Energy efficiency targets depend on building use. Residential, commercial and industrial buildings have different operating hours, internal loads and occupant needs. The envelope must control heat, air and moisture movement in a way that matches the building's function and performance pathway. Residential. For homes, the focus is comfort and reducing heating and cooling demand. Typical expectations include effective insulation, good airtightness, appropriate glazing and shading, and limiting thermal bridges. Ratings tools such as NAT-HARES and NCC requirements guide the minimum and target performance levels. Commercial. In commercial buildings, energy efficiency is strongly tied to operating cost and ongoing performance. Expectations usually include efficient glazing, controlled air leakage, well-integrated HVAC, and strong maintenance and commissioning practices. Systems like neighbours help measure and improve operational outcomes after construction. Identify risks associated with occupants' indoor activities and health and safety considerations. Improving efficiency must not create indoor health risks. Key risks include poor ventilation, build-up of pollutants, moisture and mould, and combustion byproducts such as carbon monoxide. As buildings become tighter, ventilation must be controlled and intentional, while basic safety measures, fire, services, access, remain essential. Health of occupants. Indoor air quality affects comfort and health. Common issues include irritants, allergens, odours, and moisture-related mould. Building science supports healthier outcomes by controlling moisture, selecting suitable materials, sealing to prevent pollutant pathways, and providing the right level of ventilation without unnecessary energy loss. Determine environmental and climatic conditions that impact the resilience of building materials. Local environment and climate affect how materials perform over time. Moisture, temperature swings, solar exposure, wind, and pollutants can break down seals, finishes and junctions. When durability fails, energy efficiency drops too, through air leaks, wet insulation and degraded building fabric. Moisture. Moisture is a major driver of damage and performance loss. It can reduce insulation effectiveness, increase corrosion risk, and trigger mold. Good moisture management includes correct drainage and flashing, limiting humid air leakage into cavities, and using suitable moisture and vapor control layers so assemblies can dry safely. Identify construction methods that factor in durability of materials. Durable construction supports energy performance. Key methods include installing insulation without gaps, maintaining continuity of air sealing at junctions, sealing penetrations, and protecting exposed materials from UV and moisture. Robust detailing at openings, corners, and interfaces is where durability and efficiency are often won or lost. Greenhouse and Energy Minimum Standards (GEMS) Act. Appliances and equipment also influence total energy use. The GEMS framework supports minimum energy performance standards and labeling for many products. For projects, it helps guide selection of efficient, compliant equipment, so envelope performance is supported by low-demand services and appliances. NCC 2022 Energy Efficiency. The NCC sets energy efficiency requirements for building fabric and services. It's increasingly focused on real comfort and lower energy demand, not just paperwork compliance. On site, this means specified insulation levels, sealing details, glazing requirements, and service provisions must be built exactly as approved. Quality checks often focus on junctions, penetrations, and window installation, because that's where thermal and air leaks commonly occur. How to comply with NCC. Compliance can be via deemed to satisfy, performance solutions, or a mix. Construction teams support compliance by using specified products and installation methods, keeping insulation and air sealing continuous, checking key details before linings close up. Small defects can create large performance gaps. Nationwide House Energy Rating Scheme (NatHERS). NatHERS ratings are sensitive to build quality. Changes like missing insulation, poor sealing, or different glazing can reduce the expected rating and increase heating and cooling demand. Good practice is to protect the intent of the rated design and confirm critical envelope details during construction, including insulation continuity, sealing around openings, and correct window and door specification. Best practices of energy efficiency. Best practice comes from combining measures: strong envelope performance, insulation, air tightness, glazing and shading, controlled ventilation and efficient services, efficient products and appliances. Together, these deliver comfort, health, and lower operating costs across the building life. Assess energy efficiency construction. This element focuses on how to evaluate energy efficiency during construction. The goal is to understand the main physical drivers of energy loss and select materials and systems that control those drivers reliably in real conditions. Research building science principles. Supporting energy efficiency. 4 building science concepts guide energy efficient construction: heat flow, air flow, moisture flow, solar radiation. They interact, so improvements in one area can create new requirements in another, especially around air tightness, ventilation, and moisture control. Heat flow. Heat moves from warm to cold. Insulation slows heat transfer, but only if installed correctly. Gaps, compression, and thermal bridging reduce real performance. Good detailing around slabs, roofs, and openings helps maintain a continuous thermal barrier and stabilizes internal temperature. Air flow. Uncontrolled air leakage increases heating and cooling demand and carries moisture into cavities. Air tightness is achieved through continuous air barriers, sealed penetrations, and careful junction detailing. Fresh air is then supplied through planned ventilation rather than accidental leaks. Moisture flow. Moisture control protects both health and durability. Condensation risk increases when humid air reaches cold surfaces. Effective control includes limiting air leakage, using suitable vapor and moisture layers, and ensuring assemblies have a safe drying path. This keeps insulation effective and reduces mold risk. Solar radiation. Solar gain can reduce heating demand in winter but cause overheating in summer. Passive control uses orientation, shading, glazing selection, and thermal mass to manage this balance. Solar PV and solar hot water can further reduce operational energy, but demand reduction usually comes first. Review embodied energy of the specified products or materials to evaluate the energy efficiency. Embodied energy is the energy used to make and deliver materials. Durable, long-life buildings usually reduce life cycle impacts by avoiding frequent repairs and replacements. Material selection should consider performance, longevity, and the potential to reduce operational energy over the building's life. Research heating, ventilation and air conditioning, HVAC, systems to identify levels of energy efficiency, ventilation and indoor air quality. HVAC efficiency starts by reducing demand through the envelope, then selecting efficient equipment and controls. Key factors include right sizing, zoning, effective thermostats and sensors, commissioning and maintenance. Ventilation rates, filtration, and outside air control also influence both energy use and indoor air quality. Decreased demand. Reducing demand makes everything easier. Practical strategies include better insulation, reduced air leakage, high-performance glazing, external shading, and managing internal heat sources like lighting and equipment. Lower demand allows smaller systems, lower peak loads, and lower running costs. Balanced ventilation systems for all climates. Balanced ventilation provides controlled supply and exhaust, supporting stable pressure and consistent air quality. HRV and ERV systems can recover heat and sometimes moisture, improving efficiency while maintaining fresh air. This is especially valuable in well-sealed, high-performance buildings, where ventilation is needed for health, but uncontrolled leakage is no longer providing accidental fresh air. Vapor barriers. Vapor barriers or vapor retarders limit water vapor diffusion through building assemblies. Correct use depends on climate and construction type. They must be coordinated with insulation placement, airtightness strategy, and ventilation, so moisture is controlled without trapping water in cavities. How air barriers vary from vapor barriers. Air barriers stop air movement, which is the main pathway for heat loss and moisture transport. Vapor barriers limit diffusion, which is usually a smaller pathway. A vapor barrier cannot compensate for a leaky air barrier. Good practice prioritizes continuous air tightness first, then appropriate vapor control for the assembly and climate. Decide on method of construction. This element turns principles into choices. The method of construction should support site conditions, climate, and intended use, while ensuring the envelope and services work as one system. Consistent workmanship across junctions and penetrations is critical for real energy performance. Identify site location and building position to maximize energy efficiency relating to environmental factors, climatic conditions, and use of building. Site and position influence energy demand from day one. Orientation, shading opportunities, wind exposure, and sunlight access affect heating and cooling loads. Smart placement makes passive design more effective and reduces reliance on mechanical conditioning, supporting both comfort and lower operating costs. Climatic conditions affecting building. Climatic conditions drive envelope priorities. Temperature extremes, humidity, rainfall, and wind patterns all affect detailing and material selection. In many climates, designs must retain winter warmth while controlling summer heat and humidity. Construction methods should respond to local conditions, not generic assumptions. Orientation and design of buildings. Orientation affects daylight and solar heat gain. Building form also matters. More compact shapes reduce surface area and reduce heat loss and gain. Practical controls include glazing placement, shading devices, and external surface colors. When the design supports the climate, construction can deliver performance with fewer band-aid solutions. Identify and assess energy efficiency of thermal energy, heating and cooling, air and moisture, flows throughout the building. Energy efficiency improves when key flows are controlled together. Heat flow, insulation and thermal breaks. Airflow, continuous air barrier and planned ventilation. Moisture flow, drainage, vapor control and drying. Assessing these flows helps select construction methods that maintain performance over time. Check the building for drafts and insulation. A practical priority is to remove drafts and protect insulation quality. Seal around windows, doors, service penetrations, and junctions between materials. Confirm insulation is continuous, not compressed, and not missing at corners and edges. These checks prevent comfort complaints and reduce heating and cooling demand. Airflow. Pressure differences from wind, stack effect, and fans drive infiltration and exfiltration. If supply and exhaust are unbalanced, unwanted air movement increases. Airtight construction limits uncontrolled pathways, so ventilation can be provided deliberately and consistently, improving both energy efficiency and indoor air quality. Moisture moves as vapor and as liquid water. Vapor often travels with air leakage, while liquid water can move via capillary action through porous materials. Effective construction uses drainage, flashing, capillary breaks, and moisture control layers, so assemblies stay dry and insulation remains effective. Develop strategies to minimizing unwanted air leakages. Air leakage control is one of the fastest ways to lift performance. Use caulking, weather stripping, sealants and gaskets to maintain continuity at openings and penetrations. After reducing leaks, provide controlled ventilation to manage humidity and maintain fresh air, especially in high-performance buildings. Building site. Climate and climate change. Long-term resilience supports long-term energy efficiency. Heat waves, intense rainfall, and changing moisture patterns can stress the envelope. Good responses include robust shading, strong moisture management, durable materials, and ventilation strategies that can adapt to changing conditions while maintaining comfort and performance. Planning for resilience protects the building's energy rating and reduces future retrofit costs. To finish, energy-efficient buildings come from understanding the system, control heat, air, moisture, and solar impacts, choose durable, efficient materials and equipment, and build to the approved performance pathway. When construction quality matches the intent, the result is a healthier, more comfortable, and lower-cost building to operate. Thank you for following along. I trust this video has provided the guidance you need to successfully complete your assessments. I'm CPCSUS4002 Theory, and I look forward to seeing you in the next lesson.